Welcome to the deep dive. Large language models, they're already everywhere, aren't they? Changing how we work, how we create.
They really are. It feels like these, incredible digital brains that can tackle almost anything. Poetry, code, complex questions.
Exactly. But sometimes that general ability isn't quite enough. You need something more specific.
Right, like having uh, a super smart robot that can do anything, but what you really need is an artisan. Someone who can craft that one perfect thing just for you.
That's a perfect analogy. And that's really our mission today. We're going to dig into that process, the secret sauce that turns these generalist LLMs into, well, specialized experts.
The process called fine-tuning.
Exactly, fine-tuning. So this deep dive is basically your shortcut to understanding what it is, how it's different from other ways you can customize AI, like prompt engineering or ARGI.
We'll get into the techniques that are actually making this doable for almost anyone now.
Yeah, and the whole journey, right? From idea to actually using a fine-tuned model, plus the really important ethical side of things.
Okay, so let's unpack it. Where do these LLMs start? It all begins with something called pre-training.
Pre-training, right.
Yeah.
That's the phase where they're fed just unbelievable amounts of data.
Unbelievable is the right word. Think like huge chunks of the internet, massive libraries of books, articles, everything. This huge, diverse data set is what makes them powerful generalists in the first place.
So they learn language, facts, reasoning, a bit of everything. But how do we go from that broad knowledge to the hyper-focused specialist? Is it like sending them to grad school for a specific subject?
That's a great way to think about it. Yeah, it's pretty close. We call it fine-tuning, and it's what's known as a supervised learning process.
Supervised meaning we're guiding it more directly.
Exactly. You take that pre-trained generalist model,
Right.
and you keep training it, but, and this is key, you use a much smaller, very carefully curated, and specifically labeled data set.
Labeled data. So like examples of what you want it to do.
Precisely. Often it's prompt response pairs. You show it, when you see this kind of input, produce this kind of output.
And what's actually happening inside the model? Is it just learning new facts from this smaller data set?
Not exactly. This is where it gets really interesting. Fine-tuning actually adjusts the model's internal parameters, the weights and biases deep inside the network. It's fundamentally reshaping how it works.
Ah, okay. So it's not just memorizing new info, it's changing its processing pathways.
Exactly. And that reshaping lets you do some pretty amazing things, like you can teach it to adopt a very specific brand voice consistently.
Or understand really niche jargon for a specific industry, maybe.
Yeah, without needing constant reminders in the prompt.
Oh.
Or even master complex multi-step tasks that are just too hard to explain in one go through prompting alone.
So just to clarify then, fine-tuning isn't primarily about teaching the model new information, because it got tons of that in pre-training.
That's a really crucial distinction. Pre-training builds that huge foundation of knowledge and language understanding. Fine-tuning is much more focused on what we call alignment.
Alignment. Okay, what does that mean in this context?
It's about teaching the model how to use its existing knowledge effectively for your specific purpose. How to follow instructions precisely, how to stick to certain output formats, adopt a particular style or tone.
Ah, so it knows the facts, but alignment teaches it the behavior, how to act in a specific situation.
You got it. Think about a customer service bot. The base model might know everything about your products, but it might explain it like a textbook. Fine-tuning aligns it to be helpful, concise, and speak in your brand's voice. It's tuning the how, not just the what.
That makes a lot more sense. Okay, but fine-tuning sounds pretty involved. Is it the only way to get an LLM to do what you want?
No, definitely not. And it's important to know the options because the best choice really depends on your needs, your resources, your timeline.
Right. So what are the main alternatives we should be aware of?
Well, the simplest, quickest way is probably prompt engineering.
Ah, yeah, we hear that term a lot. That's basically just getting really good at writing the input prompts, right?
Exactly. You're guiding the model's output just by crafting clever prompts. You don't change the model itself at all.
So low effort, fast results, good for maybe trying things out quickly or for tasks that aren't super complex.
Perfect for rapid prototyping, simple
Yeah.
creative tasks, yeah.
Yeah.
If you can get what you need just by asking better, that's often the place to start.
Okay, what else? I know Retrieval-Augmented Generation, or RE, is another big one.
RE, right.
Mm-hmm.
This is quite different. RA enhances the LLM by connecting it to external, often real-time knowledge sources.
How does that work? Does it do a search query first?
Pretty much. Imagine you connect the LLM to your company's internal documents. When a question comes in, The RA system retrieves relevant snippets from those documents and feeds them to the LLM along with the original question. It augments the prompt with fresh information.
Ah, okay. So the LLM uses that retrieved info to generate its answer. That sounds perfect for things needing up-to-date or proprietary knowledge.
Exactly. Customer service needing the latest product specs or querying internal knowledge bases. The key thing about RAG is it's injecting new knowledge.
Right. So prompt engineering is about asking smarter. RAG is about giving it fresh info. Where does fine-tuning fit back in? What's its unique strength?
Fine-tuning shines when you need to change the model's fundamental behavior, style, or teach it a new skill that's hard to just describe in a prompt or provide via EC.
So it's less about knowledge injection and more about capability modification.
Precisely. You're altering the model's core reasoning or response patterns for a specific domain, making it an expert in a narrow area.
And the payoff for that extra effort.
Potentially much higher accuracy on your specific task, better adaptation to niche language, more consistent output, and interestingly, sometimes it can even lead to lower costs and faster responses in production, because a smaller, fine-tuned model might outperform a larger general one on that specific task.
So quick recap. Prompting is easy guidance, RAG adds knowledge, fine-tuning changes core behavior and skills.
You nailed it. And importantly, these aren't mutually exclusive. You often see hybrid approaches using RAG and fine-tuning, for instance.
Okay, that clarifies the landscape. Now, you mentioned fine-tuning wasn't always this accessible. Let's talk about that revolution. What was the old way and why was it so hard?
Right, so the traditional method is called full fine-tuning, or FFT, and it's exactly what it sounds like. You take the pre-trained model and you update every single one of its parameters using your smaller data set.
Every parameter in models with billions of parameters. That sounds expensive.
Astronomical is more like it. Computationally, it was prohibitive. You needed huge clusters of high-end GPUs, the ones with tons of memory, like NVIDIA A100s.
Yeah.
Very expensive, very time-consuming.
And I bet storing those models was a nightmare too.
Absolutely. Training needed hundreds of gigs of GPU RAM, and then for each fine-tuned task, you ended up with a complete full-size copy of the model. Gigabytes upon gigabytes. Storage costs alone were massive.
Say cost and storage. Any other big drawbacks?
Yes, a really significant one called catastrophic forgetting.
Ooh, that sounds bad. What is it?
It's when the model, while learning the new specialized task during fine-tuning, starts to forget the general knowledge it learned during pre-training.
Oh, wow. So you make it an expert in one thing, but it forgets how to do everything else?
That's the risk. It can become less versatile, losing those foundational abilities that made it powerful in the first place.
Okay, so full fine-tuning was powerful but incredibly costly, storage-hungry, and risked making the model, well, dumber in general. That sounds like a problem.
Not a huge problem. And that's what led to the development of parameter-efficient fine-tuning methods, or PEFT. This was the revolution.
PEFT, right. What's the core idea there? How did they get around those FFT problems?
The central insight behind PEFT is actually quite elegant. Instead of updating all the model's parameters, you freeze most of the original pre-trained model.
Freeze them so they don't change during training.
Exactly. And you only train a very small number of new or specifically chosen existing parameters. Often it's less than 1% of the total parameters.
Wow, less than 1%. That must make a huge difference computationally.
Massive. Suddenly, you can fine-tune large models on hardware that's much more accessible, even high-end consumer GPUs in some cases.
And storage must be way less of an issue, too.
Dramatically less. You only need to save those tiny sets of trained parameters, which might be megabytes instead of many gigabytes for the full model.
Okay, so cheaper, smaller. What about catastrophic forgetting? Does PFT help there?
Yes, significantly. Because the vast majority of the original model is frozen, it retains most of its general knowledge. You're adding a specialization without overriding the foundation.
That sounds like a win-win-win. Lower cost, smaller footprint, preserves general knowledge. Does it perform as well?
Remarkably well.
Mm-hmm.
PEFT methods often achieve performance very close to full fine-tuning on the specific task, especially with techniques like LoRA and QLoRA. And they can even be better when you have limited training data, as they're less likely to overfit.
This really does sound like it democratized fine-tuning. It took it from something only huge labs could do to something, well, potentially anyone with a decent GPU could explore.
That's exactly what happened. It shifted the landscape, enabling smaller teams, researchers, even individuals to customize these powerful models.
Okay, let's get into the specifics then. You mentioned LoRA and QLoRA as key PEFT methods. Let's start with LoRA low-rank adaptation. What's the magic behind that one?
LoRa is really foundational in the PEFT space.
Hmm.
The core idea comes from a hypothesis, an observation really, that the change needed in the model's weights during fine-tuning is often low rank.
Low rank. What does that mean in simple terms?
It means that even though the weight matrices themselves are huge, the difference between the original weights and the fine-tuned weights can be represented efficiently using much smaller matrices.
Okay, so you don't need to calculate the giant change directly.
Exactly. Instead of training that massive update matrix, LoRa freezes the original weights and introduces two small, trainable adapter matrices, usually called A and B. The update is represented by the product of these two small matrices.
Ah, so you're only training those small A and B matrices. That's where the parameter efficiency comes from.
Precisely. Training these is way cheaper and requires much less memory.
That's clever. What happens when you actually want to use the model, though? Do these adapter matrices slow things down?
That's another elegant part of LoRa. During inference, for deployment, you can actually merge the learned adapter matrices, A times B, back into the original frozen weights.
Merge them back so the model structure doesn't change.
Right. The final fine-tuned model has the same architecture and size as the original, meaning there's no additional inference latency.
Yeah.
It's just as fast as the base model, but now specialized.
Okay, LoRa sounds great. Efficient training, no inference overhead. What about QLoRA then? How does that build on LoRa?
QLoRA, or quantized LoRa, took things a step further, pushing the boundaries of efficiency even more. It introduced technique to make fine-tuning extremely large models possible on surprisingly modest hardware, like a single high-end gaming GPU.
A single gaming GPU for models with tens of billions of parameters. How?
It uses a combination of tricks, but three key innovations stand out. First is 4-bit normal flow quantization, or NF4.
Quantization. That's about using fewer bits to represent numbers, right? To save memory.
Exactly. NF4 is a special 4-bit data type developed specifically for representing neural network weights accurately. QLoRA uses this to load the entire huge frozen base model in 4-bit precision.
So the base model takes up like 14th or 18th of memory compared to standard 16-bit or 32-bit?
Roughly, yes. It's a massive memory saving, just for load of the model.
Wow. Okay, what's the second innovation?
Double quantization. This is like an extra compression step. Even the small constants needed to dequantize the 4-bit weights back to a usable format during computation are themselves quantized.
Impressing the compression info? That sounds meta.
It is a bit. But it saves a little bit more memory per parameter. And across billions of parameters, those savings add up, potentially freeing up several gigabytes.
Okay, every bit counts. And the third one?
Paged optimizers. This tackles a common bottleneck, the memory used by the optimizer during training. Optimizers keep track of states for updating the weights, and this can spike memory usage.
Right, sometimes causing those dreaded out-of-memory errors.
Exactly. Paged optimizers cleverly use the system's main RAM, the CPU RAM, as an overflow buffer for these optimizer states. When the GPU VRAM runs out of space for them, it automatically pages them out to the CPU RAM and back in when needed.
Ah, like virtual memory management, but for GPU training?
That's a great analogy. It prevents crashes when you have temporary memory spikes that slightly exceed your GPU's VRAM capacity.
So putting it all together, QLoRA uses 4-bit loading for the base model, double quantization for extra savings, paged optimizers to handle memory spikes, and combines this with the LoRa technique of training only small adapters.
Correct. And the combined effect is truly remarkable. It makes it feasible to fine-tune, say, a 65 billion parameter model on a single GPU with 48 GB of RAM.
Which, just a few years ago, would have needed a whole rack of servers.
Easily. QLoRA has been a massive democratizing force.
Incredible. Okay, so let's say you're inspired. You want to try this. What does the actual process look like end to end, from having an idea to having a working, fine-tuned model?
We can break it down into roughly 5 main phases. Phase 1 is strategy, defining your mission.
Getting clear on the goal before you start coding.
Absolutely critical.
Yeah.
What specific task do you want the model to do, and how will you measure success? Don't just say improve customer support. Say classify support tickets into 5 categories with 95% accuracy. Be specific, be measurable.
And this is where you choose your base model too, right? Thinking about things like, is it good for coding if I need code? Does it fit my GPU?
Exactly. Task alignment is key. Use a code llama variant for code, for instance. Performance versus resources, check benchmarks, but also VRAM needs. A 7B model might need 8 GB VRAM with QLoRA, roughly. Consider context window size, the model's license, community support.
And planning your setup, local machine, cloud GPU, etc.
Right. That's all part of the strategy phase.
Okay.
Then comes phase 2, data, the fuel for your model.
And we said earlier this is super important. Quality over quantity.
The absolute golden rule.
Yeah.
A small, clean, high-quality data set of maybe just a few hundred or 1,000 examples will often beat a massive, noisy data set.
What makes a data set high quality for fine-tuning?
It needs to be accurate, obviously,
Yeah.
diverse, covering the different kinds of inputs and outputs you expect, and ideally, it should have some complexity, pushing the model to learn the nuances of the task.
And cleaning is essential, I assume. Removing duplicates, bad data.
Crucial. Deduplication. Filtering harmful content, removing personally identifiable information, PII, it's huge, and just general noise reduction. Then you format it consistently, often as JSON lines, using a standard prompt template like the alpaca format.
Okay, strategy set, high quality data prepared. What's next?
Phase 3, training, bringing the model to life. This is where you actually run the fine-tuning process.
And thankfully, there are great tools for this now. You mentioned Hugging Face earlier.
Yes, the Hugging Face ecosystem is pretty much the standard. Libraries like transformers for models, datasets for handling data, PEFT for PEFT methods like LoRA, bits and bytes for quantization like in QLoRA, crawl for supervised fine-tuning in RLHF, and accelerate for handling distributed training and hardware abstraction. They work together really well.
And during training, you need to set some key parameters, hyperparameters.
Right, things like the learning rate, how big the adjustment steps are, usually very small for fine-tuning, like 2E4 for LoRA. The batch size, how many examples are processed at once, often used with gradient accumulation to simulate larger batches on smaller GPUs. And the number of epochs, how many times you go through the data set, usually just 1 to 3 epochs to avoid overfitting.
And for LoRA or QLoRA specifically, there are unique settings.
Yes, you'll set R, the rank of the adapter matrices. Common values are 8, 16, 32, 64. LoRA alpha, a scaling factor, often set to twice the rank. And target modules, this is important. You need to tell it which parts of the model to attach the LoRA adapters to. Usually you want to target all the main linear layers, like the query, key, value, output projections in the attention mechanism.
Sounds complex, but hopefully libraries like Trill help simplify setting this up.
They do. The SFT trainer in Trill handles a lot of the boilerplate for supervised fine-tuning.
Okay, the model is trained. But how do we know if it actually worked? Phase 4.
Phase 4, evaluation, measuring success. And because these models generate text, evaluation isn't always straightforward. You need a mix of approaches.
Right, not just a single accuracy number.
Usually not. You'll use automated metrics where possible. Perplexity for language modeling fluency, BLU or scores for translation and summarization, accuracy or F1 scores for classification.
But automated metrics don't capture everything.
No, especially not nuances like tone, style, or avoiding hallucinations. So qualitative human assessment is indispensable. You need people to review the outputs for relevance, coherence, fluency, factuality, adherence to instructions, style.
That makes sense. Human judgment is key. And sometimes reinforcement learning from human feedback, RLHF, is used here too.
Exactly. RLHF is a more advanced technique often used after initial supervised fine-tuning to further align the model with complex human preferences, making it more helpful and harmless.
Okay, we've trained, we've evaluated, we're happy with the model. How do we actually use it? Phase 5.
Phase 5, production. From checkpoint to API. First crucial step, especially if you use PEFT, merge those adapter weights back into the base model.
Why is merging so important again?
To eliminate that inference latency, merging makes your PEFT-tuned model just as fast as the original, which is critical for real-world applications.
Got it. Then how do you serve it efficiently? These models are still big.
You'll typically use specialized inference servers designed for LLMs, tools like VLLM, which uses clever techniques like page detention and continuous batching for high throughput, or Hugging Face's text generation inference, PGI. These are optimized to serve many users quickly.
And then you wrap that server in an API.
Yep. Build a standard web API using something like Fast DPI or Flask, so your applications can easily send requests to the model and get responses back.
And finally, package it all up for deployment.
Containerization with Docker is standard practice. It packages your model, inference server, and API together. Then you can deploy that container using orchestration platforms like Kubernetes for scalability and reliability.
Wow, okay. So it's quite a journey. Strategy, data, training, evaluation, production. Seems manageable with the right tools, but definitely requires careful planning.
It does. And throughout that journey, there's another layer we absolutely have to talk about, the ethical considerations.
Right. This power to reshape AI behavior comes with responsibility. What are the key ethical pitfalls we need to watch out for with fine-tuning?
A major one is bias amplification. Foundation models already pick up societal biases from their massive pre-training data. Fine-tuning on a dataset that also contains biases, even subtle ones, can make the model not just learn them, but amplify them.
So if your customer interaction data reflects historical biases, the fine-tuned model might become even more biased.
Exactly. That's why meticulous auditing and curation of the fine-tuning data isn't just good practice, it's an ethical necessity. You have to actively work to mitigate bias in the data.
What about privacy? We touched on PII removal during data cleaning.
Yes, data privacy and PII are huge concerns. Models, especially large ones, can potentially memorize snippets of their training data. If that data contains sensitive PII, the model might inadvertently leak it in its responses later.
That sounds like a serious risk.
It is. Rigorous de-identification, redaction techniques are crucial. And this is where high-quality synthetic data is becoming increasingly interesting, creating artificial data that mirrors the patterns of real data but contains no actual PII, offering a privacy-preserving alternative for fine-tuning.
Okay, bias and privacy. Anything else?
Preventing harmful content generation. While base models often have safety guardrails built in during their own alignment, focus fine-tuning can sometimes inadvertently weaken or bypass these safety measures.
So someone could potentially fine-tune a model specifically to generate harmful outputs, overriding its initial safety training.
That's a risk. It means you can't just rely on putting safety filters on the model's input and output after deployment. Safety needs to be considered during the fine-tuning process itself. There are emerging techniques to try and guide the fine-tuning away from updates that might make the model less safe.
Building safety in, not just bolting it on.
Exactly. Responsible fine-tuning requires thinking about these ethical dimensions from the very start.
That's a really important perspective. So quite a journey we've been on from understanding these giant generalist models.
To seeing how fine-tuning, especially with efficient methods like QLoRA, lets us sculpt them into specialized tools.
Yeah, democratizing this really powerful capability, taking it beyond just the biggest tech labs.
It gives you, the developer or the researcher, this incredible level of control over how an AI behaves, its style, its skills.
So as we wrap up, the question for you, the listener, is really this. Now that you understand how you can shape an AI's behavior with such precision,
What truly innovative, tailored solutions could you unlock for the specific challenges you face? And crucially, how will you wield that power responsibly, keeping those ethical considerations front and center?